Hello and good afternoon friends, welcome to CEC live transmission. Dear friends, as you know that we are carrying a series on coordination chemistry, and under this series today we are going to talk on substitution in square planar complexes. And for this discussion we have once again with us in our studios Dr. Navneet Manav. Dr. Navneet Manav is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. Dear friends, today in this live transmission you have privilege to ask question from Dr. Navneet Manav on the topic substitution in square planar complexes. Dear friends, for that you need to contact her through our toll-free number. Our toll-free number is 180-110-430. So dear friends, let's carry forward our lecture and let's try to understand today's topic in detail from Dr. Navneet Manav. Hello ma'am, welcome to this lecture.
Thanks Geetika. Good afternoon to all the viewers. Today in this lecture we will be discussing substitution in square planar complexes. In the last module we discussed about substitution in octahedral complexes, and in square planar complexes, basically square planar complexes are where the coordination number of metal is 4, that is 4 ligands are arranged around the metal in a plane. That is each bond angle between ligand, metal and ligand is 90 degree. So, 4 ligands arranged like they are arranged in a square. These square planar complexes generally they are formed by D8 metal ions of cobalt plus, rhodium plus, iridium plus ion, 1 ion, and nickel 2 positive, palladium 2 positive, silver 3 plus, platinum 2, copper 3, gold 3. That is in the D8 metal ions where there is this and DsP2 hybridization can take place. So, there we have square planar complexes, and in these square planar complexes substitution in these square planar complexes is different from octahedral complexes. In a way here we are dealing with 4 ligands around the metal ion. So, when we are substituting one ligand out of the square planar, this let's say example of this Ml3X complex, square planar complex, where this is entering ligand, it substitutes this X from this, and this is that is basically in these complexes, in organic complexes, substitution reactions they take place, that is one ligand is being substituted by the another. So, this X and Y here, for example, they can be any pair of ligands, and for this the rate of this reaction is it is found to be dependent upon both the species. It is like second order rate of the reaction is second order, that is depending upon this entering ligand as well as the concentration of this reactant. So, that is second order kinetics means now in this case the mechanism depends upon both this bond breaking as well as bond making step. Whereas, in case of octahedral complexes, it was found that generally octahedral substitution takes place through this dissociative mechanism. So, in this case the mechanism that may be taking place, because it is second order kinetics following second order kinetics. So, mechanism that is taking place may be the associative or interchange associative mechanism. Here both bond breaking and bond making, they are the important steps, and firstly there is attack by the entering group at the square planar center, that is square planar center means it is in the plane. So, the attacking ligand can attack from both sides, from above the plane as well as from below the plane. So, when the ligand it attacks above the plane or below the plane, we are having this square planar and one ligand above, leading to square pyramidal geometry. This square pyramidal geometry then gets this intermediate is square pyramidal intermediate, that is 5 coordinate square pyramidal intermediate is obtained, which gets converted to trigonal bipyramidal intermediate species, and then it loses its leaving group, the ligand that is to be substituted, and then the final product is formed with the retention of stereochemistry. That is the most important factor here, is retention of the stereochemistry of the complexes there. So, that means now incoming ligand it approaches the axial site of the square planar complex to form a square planar intermediate, which gets converted to trigonal bipyramidal through Barry pseudo rotation mechanism, and in this case the reaction is complete by leaving group departing from the axial side. So, most importantly here what happens is the leaving group and this entering group, they occupy the equatorial positions of trigonal bipyramidal, while the ligands that are cis to the leaving group, they occupy the axial position. So, when the leaving group leaves and then that means the entering group takes the position, adjusts in that position, and the retention of configuration is maintained. So, the stereochemistry is the same. So, in this case, like if this is the pictorial representation where we can see that the nucleophile is attacking here, and this is a square pyramidal is formed, and after this square pyramidal is formed, this nucleophile and this ligand and the ligand this leaving group X and the ligand trans to this, they three form the they take the equatorial positions, and the ligands that are cis to this leaving group, they form the axial positions. So, here we are having square pyramidal intermediate gets converted to trigonal bipyramidal intermediate, and then when this leaving group leaves this, that is the retention of stereochemistry is there, retention of configuration is there. So, the square planar substitution reaction occurs slowly, because when the intermediate changes from square pyramidal geometry square planar to trigonal bipyramidal complex. So, that means there is loss of crystal field stabilization energy. This loss increases as we go down the group, that is in 4D and 5D series we find that the square planar substitutions are very slow, and that is why most of the complexes, most of the kinetic studies of square planar substitution are done on platinum 2 complexes, because platinum 2 complexes are found to be comparatively inert, their rate of substitution is quite low. Then because if the rate of substitution is low, then it can be easily monitored and easily studied. That is why for the study of square planar complexes, most of the examples are based on platinum 2 complexes, because platinum 2 complexes they have that rate of reaction that can be easily studied, or somewhere intermediates can also be isolated in some cases. So, in this case now when we come about this think about the mechanism of ligand exchange reactions in square planar complexes, it can follow through two routes. One is the incoming ligand attacks this square planar complex and forms the square pyramidal geometry intermediate 5 coordinate intermediate, from which this group the leaving group X leaves at the which is being substituted, it leaves, and then we get the final product where this X is substituted by ligand Y. So, in this case the rate of reaction depends upon this ML3X as well as the entering ligand, that is Y. And in case of second route is through solvent, that is firstly solvent substitutes this leaving group, that is so solvent associates to this square planar complex to form this square pyramidal intermediate, where instead of the group that we want to attach here, instead of that ligand we are firstly the solvent molecule that attaches, and then after the addition of the solvent, then this X is released, that is this bond breaking of MX bond takes place, and then this ligand replaces the solvent in the second step. In this case, in the solvent pathway, the addition of the solvent is slow step. So, it is the rate determining step. That is why in this case, if the solvent is in excess, it is pseudo second order reaction, because solvent is in excess. And when it follows this pathway, that is direct attachment of the ligand not through the solvent, it is a second order rate kinetics. So, final rate of the reaction is minus d ml3x by dt, that is Ks. Ks is this equilibrium constant when it follows this solvent pathway. This is Ky when it is through this ligand directly, y ml3x. So, the rate basically here Ks is solvent association, which so that means in that case solvent is large and constant. So, it is first order in complex only because excess of solvent is there. Now, what are the evidences? We say that in case of square planar complexes, the mechanism that is followed is associative mechanism, not the dissociative mechanism, as was found in case of octahedral complexes. Here there are certain evidences for the associative mechanism of these complexes. First is the role of entering group. So, rate of substitution is directly proportional, is found to be directly proportional to the nucleophilicity of the entering group. Nucleophilicity means nucleophile means nucleus loving. So, that means nucleophilicity basically is different from basicity, because basicity is a thermodynamic property, whereas nucleophilicity is kinetic property. It identifies like how fast the nucleophile, like how fast the rate of reaction can go. So, for most of the reactions of platinum, the rate constant is found to increase in this order. That is, in case of cyanide, it is high, then iodide, then bromide, pyridine, ammonia, and rate of reaction is found to be lowest in case of water. So, if we see clearly from here, from this series, it could be observed that the order is consistent with the polarizability of the ligand, because if we see the rate constant in these ligands, it increases with increase in polarizability of the ligand. This being highly polarizable, this is larger in size, iodide is more polarizable than bromide, hence its rate of reaction is higher. Why this is more polarizable here? With the inference, because platinum is found to be soft base. So, from this hard soft acid base theory, because soft acid soft base combines easily. So, more polarizable ligand is more is the strength of the bond with the this polarizable base, or you can say polarizable metal ion. So, the order is consistent with the polarizability of the this platinum ion. Moreover, if we can from here also, like polarizability can also be like in case of platinum, palladium and nickel. Platinum is found to be more polarizable because it is more basic, and we can find that there are more complexes of platinum as compared to palladium and platinum as compared to palladium as well and nickel. So, if we see from this reaction, that is reaction of substitution reaction of trans chloro dichloro, this is any ligand L platinum. If this chlorine is replaced by Y, one of the chlorine, this ligand remains constant in all the reactions, platinum is same, one chlorine is replaced by Y. So, if in first case, if we see this ligand is pyridine, so if it is dichloro dipyridine platinum complex, the substitution of this is studied with various ligands entering groups like PPH3 triphenyl phosphine, isothiocyanate, iodide, bromide, azide, nitrite, NH3 chloride. It is found that the rate of reaction in case of triphenyl phosphine is highest and it goes down like this. So, that means this is being the same as polarizability or nucleophilicity, more nucleophile. From the nucleophilicity parameter, we can say that more is the nucleophilicity and more is its reaction rate. Similarly, in case of triethylene phosphine, if this ligand is not pyridine, it is triethylene phosphine, same is observed, the same type of variation is observed, although this is not there, this is not available, but the variation is same, like it goes down in this order. So, that means the rate of reaction depends upon the nature of the entering group also, which indicates it to be second order kinetics. So, it is an evidence in the associative mechanism of the square planar complexes. Then second is role of leaving group. When we talk about leaving group, then that means this rate of reaction also depends upon the metal ligand bond strength, which bond is to be broken. So, in this case, like let us take the example of this di-in platinum complex, where this X is substituted by pyridine. So, this is at 25 degrees centigrade, the lability of the complex, that is the rate of reaction is in this order, like this is more labile as compared to chloride, as compared to bromide, as iodide, and this is cyanide is at the end. So, that means softer leaving groups, if the leaving group is softer, it slows down the reaction, that is it is lesser labile. The reaction is more inert when the complexation of platinum is involved with the softer ligands. So, that means what happens, like if we see at this end, like in case of cyanide, we can say this pi back bonding it increases the field strength, that is metal ligand bond strength is increased, that is why to break this bond becomes difficult, and as a result the rate of reaction decreases when there is pi back bonding is involved. So, there are some pi bonds that Y must, and moreover the Y, what the Y the entering ligand, like in this case pyridine, it will be using those p bonds that it must be approaching those positions, pi bonds, p bonds. So, that is why this depends upon the metal and ligand strength, also the ligand that is to be, that is leaving, that is lability of the ligand also plays role here. So, that means rate of reaction depends upon the strength of metal ligand bond also. So, the leaving group basically does not affect the nucleophilic discrimination, but only affects the intrinsic activity here. So, if we see in this example, if this varying this x, in this case this x varying from nitrate to chloride to bromide, iodide, azide, we can say with the nitrate the reaction is very fast, with the chloride reaction decreases, and when we reach this cyanide it is almost half of this, it is like 10 raised to power minus 3 difference is here. So, the reaction is very slow as the more softer the ligand becomes. So, the rate of reaction depends upon bond breaking also. So, from both these we can say both bond breaking as well as bond making are comparable steps. Moreover, when we studied the kinetics of the same reaction, it was found that both delta S and delta V for these are found to be negative. That means entropy factor is also decreasing, and this volume is also, change in volume is also negative. So, that means there is association, it directly indicates towards the association, because if there is association in the transition state, only then delta S will be decreasing and delta V also will be decreasing. Then there is charge effect. In case of, if we consider this complexes of platinum, where in this case we are having tetrachloroplatinate having 2 minus charge. When this chlorine, one chlorine is replaced by ammonia, we obtain this amino trichloropplatinum, 1 negative charge. When 2 chlorines are replaced by this ammonia, we get this platinum diamino dichloro and triamino chloroplatinum complex. So, that means when we take the hydrolysis of all these 4 complexes, so it could be appreciated here that this is having minus 2 charge, this complex is having minus 1 charge, this is 0 charge, and this is plus 1. So, charge varies from minus 2, minus 1, 0 to plus 1, but rate of the hydrolysis of all these 4 complexes does not vary much. There is only variation is only by the factor of 2 for all these complexes hydrolysis. So, that means if we say if we say in case of when there is a high positive charge, the platinum chloride bond breaking should be more difficult when there is high positive charge, because more is the positive charge, more would be difficult to take out a negatively charged ligand out of this. And then again with the high positive charge, it will favor the approach of nucleophiles, but because it is from this study, it is found that there is no difference in this rate of reaction of all these 4 complexes. So, it suggests that both bond breaking and bond making are of comparable importance, and there is we can say this charge on the complex has basically no effect on the rate of reaction. That means it has as the mechanism followed is associative mechanism in this case. Similarly, when we talk about steric effect is like if there are more bulky groups present on the metal complex, then there is decreases the rate of substitution. So, that means if more bulky groups on the metal complex are there, rate of reaction is rate of substitution decreases. What does it mean? Because of steric crowding, whenever there is association mechanism, the steric crowding will will result in decrease in rate of substitution, because when we are adding one more ligand to this, it will face difficulty because of more steric crowding. So, it indicates the associative mechanism as compared to the octahedral substitution, where the substitution follows dissociative mechanism. The presence of bulky groups on the metal complex in case of octahedral complexes, it increases the rate of substitution. So, that means if more bulky groups are present, the complex will follow the dissociative pathway. So, that means in case of octahedral complexes, it was observed that presence of bulky groups increase the rate of reaction, whereas in case of square planar complexes, it is found that because of steric crowding, the rate of substitution decreases. So, it could also be taken as an evidence of associative mechanism. This can be generalized from this rate constant of hydrolysis of this equation, that is hydrolysis of triethyl phosphine, bis triethyl phosphine, and this is any ligand, that is it can be pyridine, it can be 2-methylpyridine, 2,6-dimethylpyridine and chloride. So, if we are varying this ligand from pyridine to 2-methylpyridine to 2,6-dimethylpyridine, that means we are increasing the steric crowding over here. We are introducing more bulky, instead of pyridine, if it is methylpyridine, it is more bulky. 2,6-dimethylpyridine, that is one more methyl group is introduced. So, it is more bulkier than this one. So, if we can find from here that in case of cis complexes, the rate of reaction, it decreases with the steric crowding. As steric crowding increases, it was 8 into 10 to the power minus 2. In this case, when one methyl group was introduced, it was 10 to the power minus 4, and when two methyl groups were introduced, it is 10 to the power minus 6. For trans complexes, the same is observed, but the rate of decrease is not as much as in case of cis complexes. Then solvent effect. There are two types of solvent effects. One, solvents that are coordinating, which are coordinating in nature, which can coordinate to the metal ion, which can act as basis also, which they have like DMSO, water, CH2NO2 and ethyl alcohol. These ligands, these solvents, they can coordinate to the metal ligand. So, when there is the reaction, substitution reaction takes place through these ligands, it is found that the rate is independent of the entering ligand. Rate does not depend upon the entering ligand, it depends only upon the solvent. In case of DMSO, irrespective of any amount of entering ligand, it is found the rate of reaction is found to be this one. And when the solvent is water, the rate of reaction is found to be this one. When the solvent is nitromethane, the reaction, the observed rate is this one. It is independent of the amount of chloride ions. So, that means the reaction proceeds through solvent mechanism, that is solvent attaches this is excess of solvent. So, this is a pseudo second order reaction and it depends only upon the solvent. So, in another solvents where there are, it also says that this is a associative mechanism, because otherwise it would have dependent upon the concentration of the entering group as well as the leaving group also. So, solvent in which rate is dependent upon chloride, these are CCl4, methane, C4H9OH, that is in these solvent which do not coordinate to the metal ion, in the complex, the rate depends upon the concentration of chloride ion also. So, it depends upon the molar concentration of chloride ions. Then effect of metal center. The order of reactivity of series in case of isovalent metal ions like nickel 2, palladium 2, platinum 2, it varies in the order. Nickel 2 is more than palladium 2, which in turn is more than the platinum 2. So, this is the same as their tendency to form the 5 coordinate complex. So, as nickel is having more tendency than palladium, platinum, so their rate of reaction also varies in the same order. So, that is, it depends upon the stabilization of the transition state. More is the stabilization of the transition state, higher will be the rate of the reaction. Then coming to the most important effect that is being observed in this in these square planar complexes, that is being more discussed in details also, that is known as trans effect. Trans effect is, it is the effect of any coordinating ligand upon the rate of substitution of ligands present trans to them. That means, they direct any incoming ligand to a position trans to this. They facilitate the substitution of the ligand that is present trans to them. So, this effect is known as trans effect, that is effect of coordinating ligand upon the rate of substitution of the ligand that are present trans to it. This is also known as trans directing effect. So, that means, they direct the incoming ligand to a position trans to them. So, this trans effect, if we can say, in this case if this is the ligand T, so it directs the ligands to a position trans to this. So, it facilitates the substitution of this X that is present trans to this ligand. So, the depending upon the experimental series, the ability of this ligand to labelize this, we can make a series of these ligands, we can arrange these ligands in the order of their trans directing effect. It is found that CO, which is approximately CN, C2H4, they are approximately of the same level of trans effect, is having more trans effect than trialkyl phosphine, which is equivalent to hydride ions, which is more than methyl group, then thiourea, phenyl group, nitro group, isothiocyanate, iodide, bromide, chloride, pyridine, ammonia, hydroxide and water. So, from this series we can see that the highest trans group ligands are the ones which are having pi bonds between them, like CO, C triple bond O, C triple bond N, C2H4, CH2 double bond CH2. So, they are having pi, these we can say the pi acid ligands. And in this there is also one more observation that can be made from this, that is iodide is more than bromide, more than chloride. So, this can be explained on the basis of their polarizing power. This is more polarizable. Iodide is more polarizable, so it is higher in series than bromide, which is more than the chloride. So, this trans effect we can say, like this can be this can be, we can take the help of this in the synthesis of various ligands, various types of isomers with the trans or cis isomer. They can be obtained depending upon the trans ability of the this trans-directing ability of the ligand. So, for this let us take the example of cisplatin or transplatin. For the preparation of like if we start with this tetramine platinum complex, if we start the substitution of tetramine platinum with this chloro, from this series we can easily find that this chloro is having more trans effect than ammonia, which is this is having more than pyridine, which is having more than ammonia. So, trans effect of chlorine is more, chloride ion is more than that of ammonia. So, here when we substitute one ammonia with chloride, as now in this case all the amino groups are at same position. So, they can substitute any ammonia group, that is the first ammonia group can be, any group can be substituted. First this group is substituted by one chloride. So, we are having this chloride attaches to here. Now, in this complex, this trans effect now determines which other ligand will be substituted. Now, when we know that trans effect of chloride is more than ammonia, so that means chloride, what chloride will do is it will direct the incoming another chloride ligand to a position trans to it. That means, it will facilitate the substitution of this ammonia that is present trans to it by this chloride. So, the resulting product that we will be getting is trans isomer of this platinum, that is dichlorodiaminoplatinum, the trans isomer we will be obtaining. So, in another case if we are taking starting with the tetrachloroplatinum, Then upon substitution of tetrachloroplatinum, here we are having all the 4 chlorides at the same they are having, because they are having same transdirecting effects. So, the first ammonia can take any position, but after this, now when we know that the chloride ion is having more trans effect than the ammonia. So, the second, when we add second ammonia group, it will be taking the place of either this side or this side, because now the chloride is having more trans effect than this ammonia. So, that means the second ammonia will be taking the position of this chloride or this chloride, that is not the one that is trans to this ammonia. As a result, we will be obtaining cisplatin. Cis isomer will be obtained in this case, and instead of trans isomer, we will be obtaining cis isomer here. So, that means depending upon the starting material and the choice of ligand, we can synthesize the complexes on the basis of their trans effects. Whether trans isomer will be obtained or cis isomer will be obtained, that can be identified from here. Thank you so much. Next, we will be continuing in the next module. So, continuing from this slide only again, here we can say that one more thing that could be observed, if we say the trans effect of chloride is more than ammonia, we can also think that this ammonia could again be replaced. But yes, there is one more thing in addition to this, that is lability of the group. Chlorine has a greater transdirecting effect than ammonia. It is easier to replace chloride than most other ligands, because chloride is more labile than ammonia. So, that means if we have to replace add chloride, then the concentration of chloride has to be very high. So, and moreover, we can say in this case of thinking about the trans effect, whether this effect can found applications, many applications in the synthesis of various compounds, various complexes, like in case of if we know the transdirecting properties of the ligands, while synthesizing various isomers of the complexes, platinum complexes, we can keep in mind the order of transdirecting effect. Depending upon the order, the reagents can be added so as we may get the geometric isomer that we want to obtain. So, like if we want to prepare from platinum chloride this PtCl2, iodide and pyridine. So, then that means if we know the transdirecting effect of all these three, only then we can choose how this iodide and pyridine they can be added. If iodide is having more trans effect than pyridine, then if we replace this first chloride with iodide, then the iodide will be having more trans effect. The another substituent, that is pyridine, will be taking position trans to this. But if we want to have, so that means if that will result in the trans isomer. But if we want to have cis isomer, firstly we will have to take it with the iodine, then pyridine. So, this can be taken use of while preparation of various cis or trans isomer, in which series they can be used. Like in case of this nitrochloride, trichloro-nitro complex, if we add ammonia and chloride, we can obtain either cis component or trans one. It depends upon in which sequence we are adding this. If we are adding ammonia first of all, then that means nitro is having firstly if we are adding chloride or if we are having ammonia. If we add ammonia, we will be obtaining cis complex, otherwise we will be obtaining the trans complex. And this cis trans isomer, this trans directing effect can be used in the distinguishing of cis and trans isomers of platinum also, because cis platin is found to be the first drug that was used for the anti-cancer or anti-cancer properties, or that was used for the cancer treatment. So, it was important to isolate cis platin from the trans platin, and to isolate cis and trans isomers we must know whether this is cis formed or trans formed. To this there is trans directing effect can be used in the form of a Kurnakov's test, where this cis and trans isomers, they are made to react with the thiourea. When they react with thiourea, the cis isomer will give rise to this this tetrathiourea platinum. In the cis isomer, all the ligands will be replaced by this thiourea, whereas in case of trans isomer, only the ammonias will be replaced by the thiourea. As these chlorides, they are trans to each other, they remain as such, they are not replaced, because trans effect of thiourea is more than chloride. So, that means in the trans isomer, we are able to replace only 2 ligands by this thiourea. So, this test can be used to distinguish between the cis and trans isomers. Then there is trans influence also. In addition to trans isomer, we are having one term that is known as trans influence. Trans influence basically is the thermodynamic term, whereas trans effect is a kinetic term. Ligands that form strong sigma bonds or pi bond, they tend to weaken the metal ligand bond trans to the metal. That is the bond that is trans to the metal, they are weakened because of the ligand that is present trans to them, which is having higher, which is forming stronger sigma bonds or stronger pi bonds with the metal ion. So, this is the ground state property, that is they changes the bond length of the metal and the leaving group. They increases the bond length of the metal and the leaving group, and in the ground state only. So, this property is trans influence, and this trans influence is found to be depending upon their ability to form strong sigma bond or pi bond. Here it is hydride, triethyl phosphine, trialkyl phosphine rather, isothiocyanide, iodide, then methyl group, carbonyl, cyanide, bromide. Firstly, we are arranging the ligands which are having strong sigma bonds, which can form strong sigma bonds, then that is strong pi bonds that are being formed. Then they are the pi acceptors. So, the 2 factors that contribute to trans direction of the substitution, that is trans influence and the trans effect. Trans influence, as I have already told you, is the thermodynamic factor. It weakens the metal ligand bond that is present trans to the ligand, trans to the group, the trans directing group, and that too in the ground state. So, it facilitates the substitution of the ligand trans to it by weakening metal ligand bond strength. So, it changes the metal ligand bond strength and destabilizes the metal ligand bond that is present trans to it. So, it brings substitution to the position trans to it. It facilitates substitution of the ligand trans to this. Whereas, trans effect is a kinetic factor. It occurs by the stabilization of transition state. Trans influence brings changes in the ground state, whereas trans effect it stabilizes the transition state. In this case, in case of square planar complexes, the transition state basically is 5 coordinate square pyramidal or trigonal bipyramidal state. So, the strong pi acceptors like CO, carbonyl group, cyanide group, NO plus C2H4, they stabilize the transition state by accepting electron density, that is the incoming nucleophilic ligand that donates the electron density to the metal ion. So, when the metal ion transfers this electron density to these ligands through pi bonding, That is, in the transition state, when the incoming ligand will be giving its electron density to the metal ion will be rich in electron density, it will be destabilized. But if the ligands that can accept pi electron density from the metal they are present, they will accept this electron density. As a result, the transition state will be stabilized. So, the trans effect helps in stabilizing the transition state. From this, like we can say, where there is actually rate of reaction depends upon the energy of activation. So, where there is poor trans effect, low ground state ho, and there is high transition state. So, this is more activation energy. When there is sigma bonding effect, like more trans effect is there because of sigma bonding electrons. What happens is, sigma bonding effect means the ligands they weaken, they are having sort of trans influence, they weaken the metal ligand bond strength trans to them. So, as a result in the ground state, so that means in this case the energy of ground state is more. So, the difference between this ground state and transition state is lesser. So, it stabilizes the ground state. As a result, this rate of reaction will increase, and this is the effect of pi bonding. Here the ground state is not stabilized, but this transition state is stabilized because of the transfer of electron density from the complex, from the metal ions, from the intermediate to the pi accepting ligands. There are cis effects and cis influences have also been observed along with this trans effect and trans influence, but that are of not that much significance. This effect generally is observed in the form like the presence of certain ligands, they affect the substitution of the ligands that are present cis to them, that is to their cis neighbors. So, these phenomena they are independent of metal centers, but they depend upon the geometry of the metal ions. So, kinetic trans and cis effects, like for example, in this case we can say here this is a trans effect, where the trans effect is one of this complex is higher than this, and in certain cases here the cis effect basically generally is observed in the octahedral complexes, where this entering ligand, this ligand to be substituted, this is the one that will be substituted is, that is the ligand which is having cis effect. So, they will help in influence the substitution of ligand that is present cis to them. Then there are various theories of this trans effect. To justify this trans effect, various theories are there. One is polarization theory given by Grignard. This depends upon, this tells that the polarization theory we can say is same as ground state theory or sigma bonding theory. So, in this case the more polarizable ligands like thiocyanate, like iodide, they what happens is they contain pi, sometimes they contain pi electron cloud like cyanide is in this series, and there are certain less polarizable ligands like ammonia. So, the ones that are less polarizable they are lower in series, the ones that are more polarizable they are higher in series. How they weaken the pi bond, how they weaken the bond trans to them, metal ligand bond that is trans to them, that too in the ground state, that is seen in case of like in this case this is the trans ligand, it influences, it affects, there is more strength, this platinum to this ligand strength is more, as a result bond between this platinum and the ligand that is trans to this is weakened. That is, when the sigma bonding between this ligand and this metal is strong, the ligand that is trans to it will experience lesser overlapping, lesser electron cloud of this platinum. As a result, the bond between platinum and X is weakened. So, and this is observed in many cases that this bond length is more, like if we are having all these as halides, this was seen in case of Z salt where this trans effect was C2H4, and these 3 were the chlorides. What was found was this platinum chloride distance, that is trans to this C2H4 group, was found to be more as compared to these chlorides which are cis to this trans. So, that means because of the presence of this trans directing group, this bond between platinum and this X decreases. As a result, platinum X bond length increases. How it decreases? Depending upon the polarization theory, that is, if we consider firstly the ligand, that is PTX4, where all the X ligands are same. What happens in this case is all the ligands are same. So, they are surrounding this platinum from all the 4 sides. So, there is no net dipole moment, because all these ligands, they attract this platinum from the same. So, the polarization, no more polarization can take place in this case, because this will cancel by this, will be cancelled by this will be cancelled by this, because they are of equal strength. So, but when one of this X is replaced by another ligand L which is more polarizable, what happens is the more polarizable ligand, polarizable one, that means where the electron cloud of this ligand can be distorted more easily. So, platinum being 2, oxidation state is 2 plus, so it is positively charged platinum 2. So, it will attract the electron cloud of this ligand L towards itself. As a result, what happens is electron cloud of this will be towards this side, and positive charge ligand will be having, there will, in case of polarizable ligand, there will be separation of charge, that is delta negative on the side of the platinum and delta positive on the other side. As a result, this will induce dipole in this platinum metal ion, platinum 2 metal ion. As a result, what happens is platinum 2 will also be polarized, that is because this is negatively charged towards this side. So, positive charge of the platinum will be more towards this. As a result, negative charge will be towards the another end, that is towards the side that is trans to this ligand. So, what happens is here we are having delta negative charge, this ligand is also negatively charged. So, there will be repulsion between these 2 ligands. As a result, there will be weakening of this, or we can say more overlapping towards this side, there is strengthening of this bond at the expense of this bond. So, this platinum X bond is decreased, strength is decreased in the ground state. Another theory is pi bonding theory, or we can say transition state, stabilization of transition state in this case. So, in this case we can say there is the 5 coordinate trigonal bipyramidal transition state that is being stabilized. Here the electron repulsion, how the electron repulsion is decreased in the transition state, that is when suppose this is the transition state where this is the ligand, these 2, this is the ligand, this one is the ligand, and these 2 ligands are there. This is X, these are the lobes of this metal ion, this is the trans directing ligand, these are the lobes of metal, and this is the X group, that is trans to this. These are the other ligands that are present cis to this. So, in the case of a square planar substitution, this nucleophile will attack this metal here, metal complex, and it will result in 5 coordinate trigonal bipyramidal transition state, as this nucleophile will donate its electron density to this metal. So, what happens is this metal will be rich in electrons. The ligands, this trans ligand, if it is having, it can accept pi electrons, if it is a strong pi electron acceptor, it will remove the electron density from this, and it will take up the electron density as a result of d pi p pi bonding. This d pi will bond with the pi anti-bonding of this trans ligand. So, as a result, this bond strength is more, transition, this trans ligand and the metal ligand, trans directing ligand and metal, their bond strength is increased. As a result, the bond strength between the ligand that is trans to this group, that decreases, so that it can be easily broken. So, the removal of electron density is facilitated by the pi interaction of the trans directing ligand. Here dx square minus y square, dxz and dyz of the metal, they can form p bond with the pi bond, p orbital bond with the p orbital, and this will result in the stabilization of trigonal bipyramidal transition state. So, as a result what we will be obtaining is stabilization of this state. One more thing that is here is that is of importance is square planar platinum 2 anti-cancer drugs. This is cisplatin. This was first synthesized by this Pyrone. So, this is discovered by chance, it was accidentally discovered while he was working on some platinum electrodes, and it affected the E. coli, the multiplication of E. coli. This actually why we are discussing it here, because of the difference in cisplatin and transplatin. Why it is important to know about the trans effect, because we here are more concerned with the synthesis of cisplatin as compared to transplatin, which is an inactive isomer, whereas cisplatin is having the properties which can cross-link intrastrand, which can interfere in the intrastrand cross-linking of DNA, and hence prevents the reproduction of multiplication of the cells, or we can say it can affect in the anti-cancerous activity of the cells, whereas transplatin is not that. This cisplatin generally is used as a chemotherapic agent in various cancers of testicle, ovary cancer, head, neck, bladder, cervical, and so on. Then coming to this was about the trans effect of all these ligands, trans ligands, and their transdirecting effects. So, square planar substitution as well as octahedral substitution of the ligands. One more type of reactions that are taking place in the coordination complexes is the redox reactions, that is electron transfer reactions. They take place in the coordination complexes also, in addition to the substitution reactions. There can be one more there are different type of reactions in the coordination complexes. One is substitution, another is the reaction of the ligands that are present on the, that is without involving the metal ion, and the third one is the redox reactions, where there is, as the name redox, it involves reduction as well as oxidation. Oxidation is loss of electrons, reduction is gain of electrons. So, that means in the redox reaction, here the redox reaction is between the two complexes again. The redox reaction is, one is reducing the other. So, one is getting oxidized at the expense of the other. So, like for example, in this case, this complex is oxidized by losing one electron, and this one electron is gained by this complex. This is lost, this gains one electron. So, we will get this will lose, and this undergoes reduction. So, there is oxidation of this, loss of electron of this, and reduction of this at the expense of this, at the expense of each other, and at the end this will be oxidized and this will be reduced. So, these redox reactions, they are very fast reactions. They are much faster than the ligand exchange reactions. They may involve ligand exchange or they may not involve ligand exchange. There can be only electron transfers taking place without any change in the ligand. Like in this case also we can say the ligands are the same, ligand is not changing, there is no ligand exchange taking place, only electrons are being exchanged. This basically is very important in some of the biological processes like photosynthesis, destruction of toxins. These redox reactions, they are very important even in cytochromes. These in various biological reactions, basically they are based on the redox reactions, or they are based on the reduction, because they involve some metal centers also which form complexes with the enzymes. So, these basically they are the same. These reactions are basically of the interest from the biological ligands, biological complexes, bioinorganic chemistry we can say. So, mechanism, to understand the mechanism of these redox reactions, they undergo basically there are two types of mechanisms. One is outer sphere mechanism and another is inner sphere mechanism. In the outer sphere electron transfer mechanism, electron transfer takes place with no change of coordination sphere. There is no change of coordination sphere, like in this case this is oxidant, this is reductant. This oxidant will be reduced, +3 oxidation state is getting converted to +2. Here the plus 2 oxidation state is getting converted to plus 3, that is this reductant is getting oxidized, and we can see from this equation that there is no change in the ligands without any change in the coordination sphere. Coordination sphere remains intact. What changes is the oxidation state of the complex from plus 3 to plus 2. Here it is the same coordination sphere, but the oxidation state has changed from the plus 2 to plus 3 here. So, this is these are the various oxidants and various reductants. We can see in this case the rate of reaction varies with the reductants, like if we are keeping these oxidants constant with the variation of the reductants, because in this case it depends upon the transfer with which ease the electrons can be transferred. So, the rate of reaction that depends upon the ability of the electron to tunnel through the ligands from one metal to another. So, this is known, tunneling basically is moving through this energy barrier. This energy barrier, if we follow the classical physics, we can see it is like climbing the hill. But when we follow this quantum mechanical process, it is like going from this side to this side through a tunnel. Instead of climbing this hill, this is through tunneling. So, it is quantum mechanical process, that is it's with the wave nature of the ligands p or pi orbitals. So, what happens is tunneling from one side to another in case of cyanide fluoride ligands, but it does not happen in case of ammonia ligands. In case of outer sphere mechanism, we can say that there can be two types of reactions here. One is self exchange and another is cross exchange. Self exchange is like we can say in case of if both the ligands are like if we say it is between ferrous cyanide, hexacyanoferrous 3 plus and hexacyanoferrous 2 plus, that is the central metal ion being the same, that is known as self exchange. Cross exchange is when we are dealing with the two complexes having two different metal centers. Like in this case, the reaction is 100 times faster than the ligand exchange. When we see in this case the coordination sphere remaining the same, electrons, this is -4 -2 3 minus, and the oxidation state of this has changed from 2 minus to 3 minus. And in this case also it is plus 2 to plus 1, and this has increased from plus 2 to plus 3, whereas the coordination sphere remains as such. So, this is like the ligands, they are undergoing this ion pair state or sort of tunneling mechanism, and then they are reaching without any exchange of the ligands or the solvent molecules in between. So, ligand higher oxidation state, when it reaches the higher oxidation state, the bond distance between, there is one difference that is observed is like in case of if this if we can say here the oxidation state is more. So, the metal ligand bond length in this case CO-Cl bond length will be shorter as compared to this. So, only thing that changes here is metal ligand bond length. Higher the oxidation state, shorter will be the bond distance. Lower the oxidation state, longer will be the bond distance. The stronger the ligand, the less favored reduction is, because more energy is gained by losing high energy Eg orbitals. So, we can see this from this example. Then inner sphere mechanism. In inner sphere mechanism, this is involved through the bridging ligands. Like in this case, there is one inert and one labile complex generally is involved, and it was absorbed through labeled solvent molecule that this no ligand is exchanged with the from the solvent, it is from within this. So, in inner sphere mechanism, this is like this, firstly this takes place through the bridge ligand, this chloride, it will make a bridge with this, and then there will be finally exchange of this, like in this case there one bridge is formed, and from this bridge there is oxidation reduction takes place, redox takes place, electron transfer takes place through this bridge of the chloride ion that is present in this cobalt. And after this, after transfer takes place, they again break down, these ion pair break down to oxidant and reductants. So, which mechanism they will choose, they depend upon very inert metal ions, they substitute too slowly to allow bridging. So, what happens is in those cases when there is inert metal ions, they follow the outer sphere reaction mechanism path. Ligands that are able to bridge they generally follow the inner sphere mechanisms, and most metals they can undergo both type of reactions. Inner sphere is more likely if the metal is more labile, and if the metals are inert, then they will be following the complex outer sphere mechanism. And comparison with the experimental data of the known reaction that helps in deciding whether they will be following the inner sphere mechanism or they will be following the outer sphere mechanism. So, in the inner sphere mechanism it is through this bridging ligand, whereas in the outer sphere mechanism there is no bridging takes place, only through the tunneling from the bridge mechanism takes place. That's all for today's lecture. Thank you so much.
With this note, thank you ma'am. Thank you so very much for giving us a productive session. And dear friends, if you want to give your feedback for this lecture, then do write to us at info.cec@nic.in. We would be meeting again soon. Till then, take care. Goodbye. Thank you ma'am. Thank you once again.